Rn and its subspaces. This is a review of Intro to Linear Algebra. As I said, not having concrete examples will make it really hard for you to keep up with abstract proofs in linear algebra, so I decided to do some review of your previous material before we move on. Now, the approach I'm taking, however, will be a bit different than how you learned it in MAT 211. I'll try to be more conceptual. That class is a lot more computationally oriented, so you may end up passing that class just knowing how to compute things without having any concepts, and that's another reason why MAT 310 seems very hard. So I'll try to elaborate more of the concepts. There will be computations though, but it'll be slightly harder than what you did in the previous one. All right, so let's start with Rn. What is Rn? Rn is it's a set of real numbers written as coordinates, right? So an example is R2. What's R2? R2 will be pair of numbers, right? Where both of these are in R. And that's what you've been working with for your entire Calculus 1 and 2 class, right? You have coordinate system to talk about points on the plane, right? So all of these points on the plane will come with two numbers, right? So that's R2. And then you can also talk about R3. I'm not going to bother writing R3, but you know what I mean, right? R3 will be made of three real numbers. And what does it represent? It's going to represent
3D space.
The three-dimensional space, right? So that you've worked with R3 a lot in your multivariable calculus, Calculus 3. So that's what you did. Now, we're not just going to work with Rn or R2. We're going to work with these Rn with some extra operations on them. So the two operations that we're going to impose on this Rn, let's just use R2 so that it's easy to understand what's going on. So we're talking about R2 with the vector addition and scalar multiplication. And we put a parenthesis on to say that we have the set of points in the plane, and we are allowed to add 2 points, and we are allowed to multiply a real number to that point. Okay? So to explain what this plus is, if I have two elements, AB and CD, in R2, both of these are in R2, right? And then we can say that the sum of these are A plus C, and B plus D. And then to A comma B, I can multiply any real number K, and that multiplication is calculated by multiplying K to individual elements Ka and Kb. Okay. And you've worked with these kind of calculations in physics, so you already know its usefulness. So when you're doing physics 1, when you're doing mechanics, it's hard to do physics without having the concept of vectors. We call these vectors. Vectors are basically points that have extra operations in them. Okay? Now, in physics, they try to explain this as as arrows with like direction and magnitude and stuff like that. That viewpoint is also pretty useful, but here we're just going to stick with the structure of this. Okay. All right. So these two operations make this R2 into something called a vector space, and when we move on to the actual beginning of this class, after the review is over, then I'll be talking about much more general setting where you just have a set and you have this thing called addition, vector addition, and some scalar multiplication. They have to satisfy a list of properties, and if it satisfies everything, then you call that a vector space. But in the review, when we talk about vector spaces, we're only going to work with very concrete ones. The concrete ones are Rn and its subspaces. Okay, so let's talk about some subspaces. So, what's a subspace? Subspace of, so a subspace of Rn is a subset of Rn, which is closed under multiplication or addition and scalar multiplication. That's what it is. Okay. So let's talk about some examples. What's such an example? So an example of such is, let's say you have this V, which is x comma y comma z, where, let's usually, if you want to limit x, y, z to elements of certain set, you write it over here. Being able to write set theoretical notation is pretty important in this class. So like when I write these set theoretical notations, try to understand what I'm saying and see if you can write similar things, especially when you do your homework too. Okay. All right. So x, y, z, that belongs to R3, but with an additional property that x plus y plus z equal to 0. Okay. That's an example of a subspace. All right. To see that this is actually closed under addition and multiplication, I don't want to start doing proofs. So in the review portion, let's be more intuitive and not bother with proofs. We'll torment ourselves with proofs next week. So right now, let's just try to understand why this set would be closed under addition and multiplication without actually proving it. Okay, so give me an element of this space. Can you come up with an element in this space?
2 minus 4.
Good. All right, so you have 2 comma 2 comma minus 4. Okay. Give me another one.
3 minus 6.
3 what?
3 minus 6.
It's not fun. Give me something else. Another pattern.
10, 15 minus 25.
I mean, you're just adding the two. All right, let's give me something that's positive and then negative and then positive.
7, negative 10, 3.
Good. I like that. All right, so you have that, and then so we have these two sets. Let's see if the sum of these two vectors again belong to this set. Okay. Now, before I carry on, I think since only one person actually answered my question, I'm not so sure how people are understanding this. How do we know that 2 to negative 4 belongs to B? Someone else in Brett.
It satisfies the equation.
Yeah. If you do 2 plus 2 plus negative 4, you do get 0, right? So this does belong to B, right? The same deal here, right? If you have 7 plus negative 10 plus 3, you do get 0. So we know that both of these points belong to V. Okay. Now let's do the addition. What's the vector addition? Tell me the answer. 9,
-8.
-8, -1. Okay. Now, does this belong to V? Yes, because if you add these, you do get 0, right? So 9 plus -8 plus -1 does give you 0, and therefore, yes, this is closed under addition. Right? To actually prove that, we'll do such proofs later. Okay, so right now this is not really a proof. This is just to convince you that it is closed under addition. Okay, now let's think about the scalar multiplication. Scalar multiplication, let's choose a number, say 3. And let's just take the first vector and multiply it by 3. What do we get? We get 3 times 2 is 6. 3 times 2 is 6. 3 times -4 is -12. So we get this. Does this still belong to V? Yeah, it is. It is in here because if you add them, you get 0. So after doing a lot of examples, you'll probably be convinced that this is indeed a subspace of Rn. Okay. Now, on the other hand, let's say W is equal to x, y, z in R3, where you have x plus y plus z equal to 1. Okay. Give me an example of an element in W. You should participate, okay? I'm asking you a very simple question. Yeah, just say it. Yeah.
2 to -3.
2 to -3, thank you. Of course, 2 plus -3 is 1. Okay. Give me another one. Yes?
1, -1, 1.
Yes. 1, -1, 1. Right. Okay? So if you add these two elements from W, let's see what we get. We get 2 plus 1 is 3, and then 1, and then -2. Okay, is this an element in W? Does this vector belong in W? Yes or no?
No.
No, because if you add them up, what do you get? You get
2.
2. You don't get 1. So this is not in W. So as you can see, this set W is not closed under addition. Okay? In that case, the only difference between this and this is just 0 and 1. But there's a world of difference. Here, this is a subspace. So it is a vector space. We haven't defined what a vector space is, but for the review part, we will only discuss Rn itself and subspace of Rn, okay? And this is an example of a subspace, whereas this is an example of a non-subspace. It's just a subset, it's not a subspace, right? Okay. So, the second example, some trivial cases. Rn itself is a subspace of Rn. Okay, because in set theory, any set is a subset of itself. If A is a set, then any set is a subset of itself, right? So Rn is a subset of Rn, and of course Rn itself will be closed under addition and multiplication. So it satisfies all the requirements of being a subspace. So itself is a subspace. And another important, very trivial but important subspace is 0. Now, I'll try to be nice and make that 0 as a boldface, just to make it look like a set. So 0, what is 0? This is 0, 0, da da da. Everything's 0, and that's it. Okay. Which is a subset of Rn, is a subspace of Rn. Okay, so any Rn will always have these two as its subspace. Okay, so Rn itself is a subspace. The null space, no, not null space, trivial space, I think. Yeah. So. Okay. Trivial space is a subset of Rn. Okay. And the reason is, again, kind of obvious. If you take two of these, adding 0 and adding to 0, it's again 0, right? And if you multiply any number to 0, you get 0 as well, okay? Okay.
Question.
Yes.
What's the difference between subspace and subset?
Oh, W is a subset, but not a subspace.
Okay.
Right. Yeah.
Thank you.
V is a subset and a subspace. Okay.
Okay.
Any subspace is a subset,
Okay.
right? But not all subspace. I mean, most subsets are not subspaces. Okay? To be a subspace, it requires this additional property, which is harder to achieve. Right?
Thank you.
Now, what you may have observed here is that in general, subspaces of Rn are like the following. It's so if you have V equal to, say, some V in Rn, okay, where so I'm just writing V as a vector, but I'm really thinking of this as like x1, xn. And if you have, say, a1 x1 plus a2 x2, da da da, a and xn equal to 0. You have to have 0 on the other side, okay? So if you just have a single equation like that, that's going to be a subspace. Let's just go with just one. And geometrically, this is a so let's go back. I should have mentioned it right here. What's the graph of x plus y plus z equal to 0? Do you remember from Calc 3? What's the graph of x plus y plus z equal to 0? What kind of object is this? Okay, and I think some people are challenged. I'll make it multiple choice, okay? Is this a point, or a line, or a plane, or a solid? You have one-fourth chance of being right.
Plane.
It's a plane, right? It's a plane. Okay. What kind of plane is it?
3D?
Yeah, it's a 2D plane in three-dimensional space. Okay, so if I say this is x, that's y, and that's z. So one way to think of this is like you have 1, 1, 1, dot product of x, y, z equal to 0. So this dot is a dot product. It's different from the scalar product. I'm using the same notation here, but this is supposed to be thicker. That's a dot product. Because how do you calculate dot products? It's like 1 times x, 1 times y, 1 times z, and you set equal to 0, right? Now, if you have two vectors and their dot product is 0, what do we know about it?
Orthogonal.
They're orthogonal, right? So they're perpendicular to each other. So what you have is, if you have x, y, z, and you have 1, 1, 1, so that's like 1 in the x direction, 1 in the y direction, you go up by 1, so you have this vector. You have this vector here, okay, pointing that way, and then you're collecting all the vectors that are perpendicular to this. So you have a vector that's perpendicular like this, there's another one that way, but there's also like a whole bunch of vectors in all directions. So if you're having trouble imagining this in 3D, think of it like this. Suppose here's x, here's y, here's z. And then you have 1, 1, 1 being this vector here, right? It's pointed diagonally that way, okay? And then the vectors that are perpendicular to this one are all the vectors that are like this. You have all, so here's the vector, this is perpendicular, there's another one perpendicular, there's another one perpendicular. You have all of this, right? And you have vectors that are short and then long and all of these. And if you collect them all, what do you end up getting? You get an entire slanted plane that's perpendicular to this 1, 1, 1. Make sense? Okay? So the shape of this picture is a plane that passes through 0. 0 meaning the origin of the three-dimensional space. Okay? And you can use the same argument for this one and say that, oh, this is really saying that I have a vector a1 through an dotted with x1 through xn, and that gives you 0. And therefore, these two are perpendicular, so therefore, you have some direction, and you're collecting all the vectors that are perpendicular to it, so you have a group of vectors that are all perpendicular to this single vector. And in 3D, that's going to be a 2-plane. Okay? If this is a 4-dimensional, if n is 4, in 4-dimensional, that's going to be a 3-plane. So it's what's known as a linear space. So another way of talking about subspaces, they call it linear subspace. Okay. Okay. So you get that, and then in 5 dimensions, you get a 4-plane, and you always get 1 dimension less than this one, so that such space is called a. This has dimension n minus 1 and is called a hyperplane. Called a hyperplane. All right, and example 5. Now you can also have Rn with not just a single equation, for several more. You can have b1, x1, b2, x2, bn, xn equal to 0, and then you can add more. You can c1, d1, and so on and so on. You can let's just keep it short, just two of them, but you could add more. Okay. Now, if you just have two, then that's going to be dimension n minus 2. Every time you impose a condition, the dimension goes down by 1, and you impose more conditions, the dimension goes down further, right? And the problem is, we really haven't defined what a dimension is. And the intuition of the dimension should be obvious to you, right? We know that the usual plane is 2D and space is 3D, so that should be obvious. But later in this course, we're going to have a formal definition of what a dimension is. Then you really have to stick to that definition. But at the same time, you should have some intuition of what a dimension is as well. Okay. All right. So in general, all the subspaces of Rn looks like this. You have one equation or two equations or three or some number of equations, and that's imposed, and that defines a subspace. Okay.